Hello guys, welcome again to my YouTube channel, and in today's video we're going to discuss about measurement tool. If you're watching this video, I know you're familiar on measuring length using a meter rule. Now in today's video we're going to discuss about how you can be able to measure very small diameters, very small lengths using special instruments. So one of the small lengths that I'm talking about is, let's say for example you want to measure the diameter of a wire, or let's say you're trying to measure the diameter of a test tube. So let us look at some of the instruments that can be used to measure such diameters. So one of the instruments that can be used in measuring such diameters is one, and we have the calipers, and two, micrometer screw gauge. So these two instruments can be used to measure very accurate diameters of the given examples up here. So they are mostly used to measure precise measurements, and they are very sensitive. So I want us to look at how we can be able to use them in measuring these diameters. Now let us start with the first instrument, which is the calipers. So under calipers we have two types of calipers, and one of it is engineer's caliper and the other one is the vernier caliper. Now I want us to exactly look at how these two calipers are used. So first of all, we will start with the engineer's caliper. So what is an engineer's caliper? An engineer's caliper is basically an instrument that is used to measure lengths and diameters of objects that a normal meter rule cannot be able to measure. So such lengths or diameters can be, for example, measuring the diameter, the internal or external diameter of a test tube or any given cylinder. So let us just draw a small sketch of how an engineer's calipers looks like. So this is basically how an engineer's calipers look like. So this is the turning point of the engineer's caliper. So remember, you can turn these engineer's calipers all the way around, and you can use this part here to measure the external diameters, and you can also use it to measure internal diameters depending on how you turn it. I can just show you an example on how you can use this instrument to measure internal and external diameters. So let us say for example this is our cylinder here, and you want to measure the external diameter of this cylinder. So what you're going to use, what you're going to do is you're going to use this part here. This one can be used to measure the external diameters of bodies, whereby you can just stretch it like this. You stretch it out and then you place it. One part should be laying at this point and the other part should be laying at this point here. So remember, having doing this, you have measured the distance from this part to this part. Now you can take this engineer's caliper and then take it to a meter rule. Let's say for example this is our meter rule, and these are the scales of the meter rule. So you can just transfer this length, then take it to the meter rule, and then you can be able to measure the diameter of this instrument. So it's just a matter of transferring this diameter and then confirming the distance of that diameter using a meter rule. And that is the simplest way on how you can use an engineer's caliper to measure external diameter of a cylinder. Now what if you want to measure internal diameter of a cylinder? What are you supposed to do? So let me clear all this. Remember previously we were measuring the external diameter from this part to this part. Now this time we want to measure the internal diameters from this part to this part. This is the internal diameter. So what do you think you should do? What you need to do is you need to overturn this engineer's caliper to the opposite direction, and so it will look something like this when you overturn it, whereby the sharp part will be here and the other part will be here. So having done that, you have overturned this engineer's caliper so that it can be able to measure the internal diameter of this meter rule. And then just as before, for you to transfer this measurement, you need to use a meter rule. So you take your meter rule, let's say for example this is our meter rule, then these are the scale. This is the scale of the meter rule. You just need to transfer this here, and then you can be able to measure that diameter. So for you to use an engineer's caliper, you need to use it together with a meter rule for you to be able to transfer that measurement. So an engineer's caliper is basically used to measure diameters or length of objects that cannot be easily measured using a normal meter rule. So that is the simplest way on how you can use an engineer's caliper to measure length. Now, next we need to look at this one, which is the Vernier's caliper. So I can just draw a sketch on how a Vernier's caliper looks like. Let me clear all this. So this is just a simple sketch of a Vernier's caliper. So let us just name a few parts of this Vernier's caliper. So this first part here, this one, is referred to as the main scale. This part here, the sliding part, is referred to as the Vernier scale. So this part here is referred to as the outside jaws. This part here is always referred to as the fixed jaw. It is fixed. And then this part here is referred to as the inside jaw. So it's important for you to take note that this instrument here, it measures its length in unit called centimeters. Make sure you take note of that, because a lot of people get confused and write their answers in millimeter, but instead it's supposed to be in centimeters. Now, let's say for example you have a test tube. Where do you think you're supposed to place it? Remember, this inside jaw is used to measure inside diameters, and this outside jaws is used to measure the outside diameters. So you can use this inside jaw to measure internal diameters and the outside jaws to measure the external diameters. So this sliding jaw carries the Vernier scale, as you said, and it's important to take note that the Vernier scale usually has a length of 0.9 centimeters. So if you measure the length from this point to this point, then this length is exactly 0.9 centimeters. And remember, this Vernier scale has 10 equal divisions. So if 10 divisions is equals to 0.9 centimeters, what about 1 division? So it is like 1 multiplied by 0.9, then you divide by 10. So 1 division is equal to 0.09 centimeters. So that is equivalent of 1 division. So when you talk about 1 division, is like the length from this part to this part on the Vernier scale. Remember, we're not talking about this main scale. These lines here on top represents the main scale, and this ones on the bottom represents the Vernier scale. That's why I've differentiated them by using the red color. So the distance from this part to this part on the red scale is exactly 0.09 centimeters. Now, what do you think will be the length of the main scale division? Let's say the distance from here to here. Now remember, these ones are exactly how they're supposed to be. So the distance from this point to this point is exactly 0.1 centimeters. So the difference between the main scale division, which is 0.1, then you minus by the Vernier scale division, which is 0.9. Remember, these ones are in centimeters. The difference between them we'll get is 0.01 centimeters. And now this one is now referred to as the least count. So in simple terms, least count is the difference in length between the main scale division and the Vernier scale division. So the main scale division here is 0.1. The Vernier scale division here, as we calculated here, is exactly 0.09. So the difference between the two gives you the least count, and that's how you define least count. Now, having known all that, let us now see on how we can use this instrument to measure length or diameters of objects. So let me clear this. Now remember, we said we always use these jaws to measure the diameters. So let's say we use the outside jaw to measure external diameters, and for you to measure it, you just need to place the thing you need to measure here, and then you just move this Vernier scale until it touches this part. And remember, this fixed jaw is also supposed to touch this part. Now you're supposed to measure this diameter. How are we supposed to use this instrument, or what are some of the rules that you're supposed to follow for you to be able to measure the lengths of these objects you want to measure using this Vernier caliper. In your exams, you'll see something like this. It will be something like this, and then on top, so let me represent it with a white color. So on top, you'll have a scale like this, and then on the bottom, you'll also have a scale. So let me use red. On bottom, you'll also have a scale like this. So in exams, they'll mostly represent the question like this to represent this Vernier caliper. Now, how are you supposed to interpret this? So this one basically shows that on top, this top scale here represents the main scale, and on the bottom here, this scale here represents the Vernier scale. So this is the main scale, this scale here that runs from this point to this point, and this down here is the Vernier scale, the scale that runs from this point to this point. Now combined, you can be able to calculate the length of any object or the diameter of any object. Now how are we supposed to know the length of this? So I can just give you a clear example of a representation of a question. So our first example will look like this. Now let us say, for example, this is our example here, and we want to measure, let's say, the diameter of this object. Remember, after, let's say, for example, we've placed our object, this is the final reading, this is the main scale, the one on top, this one here, and this is the main scale, and down here, this is the Vernier scale. Now how are we supposed to calculate this? So let us start with, remember we have two scales, so we need to know the distance or the length of the two scales, and then we add them together. So let us do that. So let us start with the main scale. Now how can you be able to read the values of the main scale? So for you to be able to know the length of the main scale, what we normally do is we always look at the value that is immediately behind the 0 mark of the Vernier scale. So this is the value of the Vernier scale here, the 0. So you need to look at the value that is immediately behind it. So this is 2, this one will be 2.1, and this value here that we want will be 2.2. So the main scale is exactly 2.2. So you can write it, well, this is 2.2. And remember, as we said before, the unit is in centimeters. That's it. We are done with the main scale. Now, how can you be able to know the value of the Vernier scale? Now, for you to be able to know the value of the Vernier scale, what we normally do is we look at the line to which the Vernier scale has exactly coincide with the main scale. For example, this one here, it has not coincide with the top line on the main scale, so this one is a no. This one also, it has not coincided, so this one is a no. This one here also has not coincided, this one is a no. This one here has not also coincided, this one is a no. But this one here, it has coincided exactly with the main scale, so this one is a yes, because if you look keenly, this line here and this line here, it's like a continuous line, meaning it has coincided. And remember, we always look at the first line that coincides with the main scale, not the second one or the third one. We always look at the first line that coincides with the main scale, and this is the line that we're looking for. So remember, we'll take the value of the Vernier scale only, and this value here is 4, because here is 0, 1, 2, 3, 4. So this value is 4. So you can write Vernier scale is equal to 4. Now, remember, we are not done yet, because in Vernier scale, we do not take the value directly and then add it together with the main scale. So what we normally do is we take the Vernier scale and then we multiply it with the least count. Remember, previously we talked about the least count, whereby we said the least count is the difference between the length between the main scale division and the Vernier scale division. So that is like the smallest unit of measurement of a Vernier caliper, and we calculated it and found out that the least count is equal to 0.01 centimeters. So for you to be able to calculate the Vernier scale, you need to take this value and then multiply it with the least count, because that is the values on the decimal places from the main values. So this is the main values, and this will be the value of the decimal places. So you can calculate that, whereby we will take this value here, this 4, and multiply it by the least count, which is 0.01, and this now will be in centimeters. So if you calculate this, you'll get a value of 0.04 centimeters. Now the final answer of this will be, you take these two and add them together. So the Vernier scale, the main scale was 2.2 centimeters, and the Vernier scale is 0.04 centimeters. When you add them together, you find a value which is exactly 2.24 centimeters, and that is how we calculate the diameter using a Vernier caliper. And I can just give another example. You can do another example, the final example, and then I'll give you one. You try it for yourself. So let me clear all this so that I can draw the next example. So this one will be example 2. So this is example 2. So now let us say, for example, you want to measure the diameter of the Vernier caliper, and this is the value that you've gotten. How can you be able to calculate this? For you to calculate this, we have two scales. So we have the main scale and we have the Vernier scale. So let us start with the main scale. The main scale is this scale on top here, and the Vernier scale is this scale on the bottom here. So what is the main scale? How can you be able to calculate the main scale? So the main scale, we say that we always look at the value that is immediately behind 0 on the Vernier scale. So this is the Vernier scale and this is the 0 value. So we will look at this value behind it here. So the value behind it is 0. So you can write the main scale as 0 centimeters. What about the Vernier scale? The Vernier scale, we say that we look at the value that coincides exactly with the main scale. So if you look at this value is not coinciding. So this is a no. This value is also not coinciding. So this is a no. This one is not coinciding. This is a no. This value is coinciding. So this is a yes. So what value is this? This is 0, 1, 2, 3. So the value that coincides with the Vernier scale is exactly 3. And we say that in Vernier scale, we take the value that we've gotten and multiply it with the least count. And the least count is exactly 0.01 centimeters. So the value of the Vernier scale is 3. So we'll take this 3 and multiply it with the value of the least count, which is 0.01, and you'll get a value of 0.03 centimeters. So now you need to take the Vernier scale and then you add with the main scale. So it will be 0 plus 0.03. Now remember, the unit for this is in centimeters, and you find your answer as 0.03 centimeters. And this is your answer. So you can try out this question and then leave your answer in the comment below so that we know if you have understood or not. So now let us talk about something called the zero error in Vernier caliper. So we always have two types of zero errors, one of which is the positive zero error, and we also have the negative zero error. So a lot of students get confused between these two. They don't know which is which, and here I will exactly show you the real example, the real difference between these two. So what is the difference between the positive zero error and negative zero error? Or first of all, before we go to all that, what is actually a zero error? What do you understand by a zero error? So one thing that you're supposed to know, that it is very important that whenever the jaws of a Vernier calipers are closed, let's say this Vernier scale is completely shut down, whereby this part and this part touch each other. So what's supposed to happen is that the zero mark on the Vernier scale, this zero mark here, is supposed to coincide with the zero mark on the main scale. So if there's an issue somewhere, or let's say the zero mark of the vernier scale does not coincide with the zero mark on the main scale, then that means that there's a zero error somewhere. So basically what is supposed to happen is this: whenever you shut down this instrument, and let us say for example this is our common line, then the zero mark on the main scale, this zero mark is supposed to coincide with the zero mark on the vernier scale here, and the other values will follow like that. So they're supposed to align with each other like this. So if there's a situation whereby this zero mark does not coincide, let's say for example it is in front or back, then that is where the zero error occurs. So zero error occurs only when the zero mark of the main scale does not coincide with the zero mark of the vernier scale. So which is the positive zero error and which is the negative zero error? That is the question that you're supposed to ask yourself. So let us take an example of the vernier scale, for example, for us to understand this. So if the vernier scale is behind the zero mark, then that will be a negative zero error. So a negative zero error is whereby the vernier scale is behind the zero mark. So we take this one as the common point. So if the vernier scale is behind, then that is a negative zero error, this one here. And if it is in front, in case if it is in front, let us use another color. If it is in front like this, then this is a positive zero error, and this one is here on top. So if it is behind, then that is a negative zero error. If it is in front, then that is a positive zero error. So we can give an example, a diagram example of a zero error, and then we calculate the zero error. So let me draw it down here. So this is our main scale, and now let us draw the vernier scale down here, and this is our vernier scale. So if you look closely, our vernier scale is right in front of the zero mark of the main scale, so it is in front. And you say that if it is in front, then that is a positive zero error. So it is very important to take note that a positive zero error, like for example this one here, this is a positive zero error because the zero mark of the vernier scale is right in front of the zero mark of the main scale. So this value always gives a value that is higher than the actual value. Let's say for example you are trying to measure this diameter here, you'll get a value that is more than the actual value. So it is very important to always check that your vernier caliper does not have a zero error before measurement, because if you do your measurement and the vernier caliper has a zero error and you did not take note of that, then you'll find a value that is either higher or lower than the expected value. So a positive zero error like this one here, the value is always higher than the actual value. A negative zero error, the one that the vernier scale is right behind the zero mark of the main scale, the value will always be lower than the actual value. Whenever you are given a vernier caliper and then you're told that that vernier caliper has a zero error of, let's say, something, so the actual value that you'll find after measurement, you're supposed to subtract it. If it's a positive zero error, you're supposed to subtract that zero error to the readings that you'll find. If it's a negative zero error, then you're supposed to add that value. So it's like the opposite. If it's a negative zero error, you're supposed to add it. If it's a positive zero error, you're supposed to subtract it. It's like you're doing the opposite of the actual value given. If it's positive, you minus. If it's negative, you add. That is the simplest formula of knowing this. So let us look at this example here. So let us try to calculate the zero error here. So what do you think is the zero error in this measurement? So the main scale here is 0.2 because this is 1, this is 1, this is 2. So the main scale is 0.2 centimeters. What about the vernier scale? So the vernier scale, we always look at where it coincides. So where does it coincide? So it coincides here. Here is where it coincides. So it coincides at exactly 9. So the Vernier scale is 9. And we say that the Vernier scale, we usually multiply it with the least count. And the least count is 0.01. So if you do that, you'll get 0.09 in the Vernier scale. Then you take that value and then add it to the main scale, which is 0.2, and you find your answer as 0.29. So this is the zero error. And remember, you're supposed to indicate whether if it is positive or negative. So in this case, because it is right in front of the zero mark of the main scale, then that is a positive zero error. So if you do your measurements, your final answer, you're supposed to minus this value because it's a positive zero error. So you're supposed to less the value of the zero error. It is very important to take note of that. Now let us look at the next scenario of a negative zero error. So this is a very good example of a negative zero error, whereby, as you can see, the Vernier scale is behind the zero mark of the main scale. So what is the value of this zero error? So we just need to look at the main scale. So the main scale is obviously 0 because it is way behind 0. And then the Vernier scale, we just look at the value that coincides exactly at the main scale. So this one does not coincide, this one does not coincide, this one no, this one no, this one yes. And I want you to take note that even this value coincides with the 0 mark, I mean the main scale, but you're not going to use it because it is way in front of this one. So we usually take the first value that coincides with the main scale. So it's very important to always start from this point going this way whenever you are reading the Vernier scale. Take note of that. So we will take this value, and this value is exactly 1, 0, 1, 2, 3, 4. So the Vernier scale is exactly 4. So we said under the Vernier scale, we usually multiply it with the least count. The least count is usually 0.01 in a Vernier caliper. So this 0.01, we multiply it with the value that we've gotten, which is 4, this one, and then you'll get exactly 0.04 centimeters. So this is a negative zero error. So you need to indicate it by writing here a negative. So this, your answer is negative 0.04 centimeters. So this is the zero error. So when you do your measurements and you find your final answer, you need to add it with this one, because a negative zero error usually gives you a value that is less than the actual value. So you are supposed to add this value so that you find the correct, accurate answer. Always take note of that. So that is all about the Vernier caliper. I want us now to look at the micrometer screw gauge and how to use it. So I will just draw a sketch of a micrometer screw gauge here. You see how it usually looks like, and then we will discuss it in details on how you're supposed to measure your diameters using this instrument here. So this is just a simple representation of a micrometer screw gauge. Sorry about my drawing, but I hope you get the point. So here at this point, this part is always, let me change the color. So this part here is known as the anvil. It's called the anvil. And then this part here is called the spindle. This one is the spindle. Now this scale here is referred to as the sleeve scale. Now I want you to take note of this sleeve scale. You'll realize that it has two portions. We have one on top and one on the bottom. So here at the bottom we can pick, let's say for example, this one here. This one represents 1/2 millimeter unit. So this one is like a half a millimeter. And then this point here is the sleeve scale division. This one's on top. These are the sleeve scale division. Now this one here is a moving part. It rotates round. So this one here is a thimble scale. So this one here is the thimble, and this part here at the back is called a ratchet. So this is all the parts of a micrometer screw gauge. Now I want us to look at how we're supposed to measure or how you're supposed to use this instrument here. So this micrometer screw gauge can be used to measure very small diameters, let's say a diameter of a wire, very small diameters. It can measure them very accurately. So it is very important to take note that a micrometer screw gauge measures its unit in millimeters. Unlike the Vernier caliper, which we discussed earlier, it measures its unit in centimeters. So this one measures in millimeters, meaning it is very precise. It's very precise. It can measure very small amount of unit. So the fact that it measures in millimeters makes it very useful in measuring very small amount of diameters, very small lengths, because it can measure them accurately with no errors, as long as you know how to use it. So the sleeve scale, this one here, has linear scale in millimeters. And the thimble scale, this one here, it's actually circular. It's supposed to be circular, but I know you've seen it. I know you know how it usually looks like. So the thimble scale has 50 divisions. It always has 50 divisions. So what do you think is the use of this ratchet? So the use of this ratchet is just there to prevent you from exerting too much pressure on the thing that you're trying to measure. So like the Vernier caliper, the micrometer screw gauge here is where we place our thing that we want to measure. We always place it here, and then we read the readings here. So let's make sure that one end it touches this part and the other end touches this part. So it is very important to take note of that. So one point touches this part and the other point touches this part. So this ratchet is just there to prevent you from exerting too much pressure on the thing that you're trying to measure. So remember, if you twist this too much, then you'll be exerting too much pressure on the thing that you're trying to measure the diameter, because this thing keeps on moving this way. So if you rotate this thing too much, then you'll be exerting too much pressure on this. So this ratchet usually clicks whenever it reaches its end point, and when it clicks, you're not supposed to exert extra pressure on it. It means that that is the end point and you're supposed to take the measurements. So now remember, we said that this thimble rotates, and when it rotates, it moves this spindle this way. So the distance covered by this spindle in one complete revolution or rotation of this thimble scale is what is referred to as a pitch. So a pitch is basically the distance moved by the spindle in one complete rotation of the thimble scale or the thimble. So when you rotate this thing once round one complete rotation, the distance covered by this spindle is what is referred to as the pitch. So we usually say that in one complete rotation of this thimble scale, this pitch, this saddle, I'm sorry about that. So this saddle usually moves to for a distance of 0.5 millimeters. So 0.5 millimeters is the actual pitch of a micrometer screw gauge, whereby in one complete revolution of this thimble, this pitch moves at a distance of 0.5 millimeters. So this is the pitch. I remember I told you about the thimble scale, and I told you that the thimble scale usually has up to 50 divisions, but not all of them, because we have some thimble scales that goes up to 100 divisions. So it depends. So for example, if the micrometer screw gauge that you have, the thimble scale has 50 divisions, then it means that, and the pitch is 0.5. Remember I said the pitch is the distance covered by the spindle in one complete rotation of the thimble scale. So let's say for example 0.5 millimeters. So that is the pitch. The distance covered is equal to 50 divisions of the thimble scale, because we said the thimble scale has 50 divisions. So what about 1 division? So what will 1 division be? So if you cross multiply, then it will be 1 multiplied by 0.5, then you divide by, so here is a point, divided by 50, and you'll find your answer as 0.01 millimeters. So this is the least count or the least measurement of a micrometer screw gauge. Remember, I've used millimeters here. Take note of that. So the least count of a micrometer screw gauge is 0.01 millimeters. Now, what if your micrometer screw gauge has 100 divisions? What do you think will be the pitch? So usually, if your micrometer screw gauge has 100 divisions, then it means that it has a pitch of 1 millimeters. So if your micrometer screw gauge has a 100 division, then its pitch will be 1 millimeters. So it is like double this. So it depends on the number of divisions of your thimble scale. If it's 100 division, then the pitch is 1, and if it is 50 divisions, then the pitch will be 0.5 millimeters. So it is very important to take note of that. Now let us look on how you can calculate the diameters or measure the readings of a micrometer screw gauge. So in micrometer screw gauge, we have two scales. We have the sleeve scale and we have the thimble scale. So let us give a few examples of how you can be able to calculate the diameters using these two scales. So in your exams, they will not draw you the whole micrometer screw gauge in most cases. They'll just draw a horizontal line like this. So this horizontal line will represent the sleeve scale, and then another vertical line from this point. So this vertical line will represent the thimble scale, and then they'll just put the values here and other values here, and then you're told to, let's say, calculate the diameter of the given thing that is being measured there. So let me give you one or two examples on how to use this micrometer screw gauge to measure diameters. So let us say you've been given an example like this. You're told to find the diameter of something that is being measured here. So what do you think you're supposed to do? Remember, here we have two scales. One of the scale is the sleeve scale, so this one here. And here we also have another scale here, which is the thimble scale. How can you be able to identify the diameter of this marble or this thing that is being measured here? So for you to be able to measure the thing that is being measured here, so let us start with the first one. So we have the sleeve scale. Let's start with the sleeve scale. So what is the value of the sleeve scale? So we always look at the value that is immediately behind the thimble scale. So let us say this one is 10, and make sure you take note of this. Each value represents 1. So if this is 0, then this is 1, 2, 3, 4, 5. So don't make a mistake whereby you take this one as a 0, 0.1, 0.2, 0.3. No. If this is 0, then this one is 1, 2, 3, 4, and 5. And the values of these are in millimeters, not in centimeters. And then down here is whereby it's always at the middle. We have another scale here at the middle, like this. So these ones at the middle, basically they represent, I think I told you before, they represent half a millimeter. So it is halfway between a millimeter, all this here. So let's say, for example, you're trying to measure the diameter of this. So the sleeve scale, we will start with 10. So this one is 11, 12, 13, then 14. So the sleeve scale is 14 millimeters. 14 millimeters, not centimeters, it is in millimeters. Now let us go to the next one, which is the thimble scale. So what do you think is the value of the thimble scale? So the thimble scale, we always look at the value that coincide with the main line, this line here, the value that will coincide exactly at the end. And in our case here, it is 20. So 20 is the value on the thimble scale. So we have gotten our answer as 20 on the thimble scale. So what do we do next? What we do next is we take this value and multiply it by the least count. And the least count of a micrometer screw gauge is actually 0.01 millimeters. This is the least count. So we take this value and multiply it with the least count. The same way we were doing under the Vernier caliper when we were calculating the Vernier scale. So in micrometer screw gauge, we also take the value of the thimble scale and multiply it with the least count, which is 0.01 millimeters. And we will find if you take 20, you multiply by 0.01, so your final answer will be in millimeters. Remember, this one does not have a unit. It does not have a unit here. It is just like that. It will only have a unit when you multiply it with the least count value, and you will find your answer as 0.2 millimeters. So you are supposed to take this value of the thimble scale and then you add it with the value of the sleeve scale, and you'll find your answer as 14 plus 0.2, and your final answer will be 14.2 millimeters. So that is the diameter of that thing that you're measuring. So let us look at another example. Now let us say, for example, you are given these measurements and you're told to calculate the diameter of that thing that is being measured here. Let us say if it's a marble or something like that. So what do you think would be the value? So as we always do, we start with the one scale after another. So let us start with the sleeve scale. So what is the value of the sleeve scale? So let us start from here. So this is 0, this is 5, this is 10. So it means that this is 5, 6, 7, 8, 9, 10. Or this one is 5, 5.2, 5, 6, 6.5, 7, 7.5, 8, 8.5, 9, 9.5, 10. So this is 10, right? This is 10 here. So this is 10.5, 11, 11.5, 12, 12.5. Remember, this is visible, so we always take this value. So the value of the sleeve scale is 10, 11, 12, but it is 12.5. Make sure you take note of that. So this is 12.5, and this unit is in millimeters. So make sure you write millimeters. Let us go to the thimble scale. So what do you think will be the value of the thimble scale? So let's look at the value that aligns with this line here. So the value that aligns with it is this one here, which is 45. So the value is 45. So what we normally do is we take this value and multiply it with the least count. So we take 45, then we multiply it by 0.01, and then the final value will be in millimeters. So what do you think will be the answer? So this is a bracket. What do you think will be the answer? So if you take this one and then you multiply by this, it's like dividing it by 100, right? So you just bring these two zeros here, and then your final answer will be 0.45 millimeters. That is your final answer. So we always take the thimble scale and add it together with the sleeve scale. So your final answer will be 12.5. You add it with 0.45, and your final answer should be in millimeters. So if you add this, you'll get 12.95. So 12.95 is your final answer. This is your final answer. So let me give you an exercise to do. So try out this one. So this is exercise 2. The previous one was exercise 1. So in the comment below, just write your answer as exercise 1 is equals to and exercise 2 is equals to. So exercise 2, try this question. So I want you to try out this question as exercise 2 and then comment your answer in the comment section below. So now let us look at zero error under micrometer screw gauge. It is very much similar as the Vernier Calipers. So let us look at it. So what do you think is zero error when it comes to micrometer screw gauge? So the zero error in Vernier caliper, we say that a zero error in Vernier caliper happens when the zero mark in the Vernier scale does not coincide with the zero mark in the main scale. Now what about a micrometer screw gauge? So a zero error in micrometer screw gauge will only occur when the zero mark on the thimble scale does not align with the center line. So it has to align with the center line. So let's say, for example, this is just an example. Let me just draw a quick example of what I'm talking about. Just a diagram representation of what I'm talking about. Let's say this one is the center line, this line. This is the line we're talking about, this one. This is the center line. This center line is supposed to align with the thimble scale, with the 0 mark of the thimble scale. So if this is the line, then this thimble scale 0 value is supposed to align with it exactly like that. So in case there's disalignment of this 0 value with this center line or this main line here, then that micrometer screw gauge has a 0 error. So depending on the position of this 0 value, if it's on top, it will have its own 0 error. If it's on the bottom, it will have its own 0 error. Remember previously we talked about 0 error, the types of 0 error. We have 1, the positive 0 error, and 2, we have the negative 0 error. So which is which? In this case here, scenario 1, there's no 0 error because the 0 mark coincides exactly with the center line. What about a positive 0 error? When does a positive 0 error occur? Let me use another color. So when will a positive 0 error occur? A positive 0 error will occur when the 0 mark is above the actual center line. So let's say your 0 mark will be here on top. So instead of being here, 0 mark will be here. So this one will be referred to as a positive 0 error. Now what about a negative 0 error? When will a negative 0 error occur? So a negative 0 error will be the opposite of a positive 0 error, whereby your 0 mark will be below the center line. So it will be down here. So this one is referred to as a negative 0 error. This one here. So it's very important to take note of these two differences. And previously I think I told you if you have a positive 0 error, then it means that you are supposed to minus the actual value that you'll find in your final measurement. If you have a negative 0 error, what you're supposed to do is to add the final value that you'll find in your measurement. So that is very important to take note of. So the formula you can use here is, if it is positive, you just do the opposite, you minus. If it is negative, you do the opposite, you add. And you find the actual measurement. And that is all about a micrometer screw gauge. Now let us look at the final part of this topic, which is referred to as the oil drop test, the oil drop experiment. Let us look at the oil drop experiment. So the oil drop experiment can be used to demonstrate the extent of environmental damage caused by the oil spillage from ships. So when oil drops, let's say in the sea, so the oil drops, let's say for example in the sea, what do you think will happen? We all know that oil does not mix with water, so it will form a layer on top of the water. So what you can do is to find the volume of that oil that is floating above the water. And how can we be able to do this? So let me just give you a small demonstration of what normally happens. So let us say for example this is our surface here, and then on this surface, let's say for example there's a spilled oil on top. There's a spilled oil on top of the surface. Okay, so this one here is a lycopodium powder. Make sure you comment below on the comment section telling us why you use a lycopodium powder for this practical or for this experiment. So comment below why we normally use a lycopodium powder. So those are 3 assignments. So tell us why we normally use a lycopodium powder in this experiment. So what do we do in this experiment? What is the first thing we do? So the first thing we do is we measure the average diameter of the patch. So let's say for example this is the oil patch. So we measure the average diameter of the patch. So let's say for example we find the first diameter as D1, and the second diameter as D2, and the third diameter as D. After finding this, what you do is you find the average of these 3. So it will be D1 plus D2 plus D3, and then you divide all by 3. What next we need to do is to find the area of the patch. Now we always take this one as a circle because it's almost a circle, but it's not a perfect circle. It's somehow spherical, but we take it as a circle. And we know the formula of finding the area of a circle is, so area is equals to pi r squared, right? But remember, in this case, we were using diameters. And this diameter, let's say the final diameter, we represent it as d. So this is the d, the average diameter of these three diameters. So we represent the average diameter as d. And area of a circle is pi r squared. So we can represent this one as pi. And then if we use the d, this one, because we are not using the radius, if we use this d, it will be in brackets d. We all know to find the radius, we take diameter divided by 2, because 2 radius makes a diameter. So this will be d divided by 2, and then all squared. So doing this, we will have found the area of the patch. So what we normally do, or what we normally say, is that whenever an oil patch is formed, whenever this oil drops on a surface, what normally happens is that it forms like a sphere. We always represent it as a sphere. So there will be a thickness down here, whereby this thickness will just be floating on top of the water like that. So this thickness is referred to as the height. And remember, this height is what we are trying to find. Okay, this is the height that we're trying to find. And we all know that volume. So remember, this one forms like a cylinder, and we all know the formula of finding the volume of a cylinder. Let's say this one is the oil patch. So we represent it as a cylinder, whereby this is the cross-section area on top, this one here, and then this one is the height. The distance from this part to this part is the height. We all know finding the volume of this cylinder, we always take the cross-section area. The cross-section area, we multiply it by the height. So volume is equals to cross-section area multiplied by height. What if you're trying to find the height? So if you're trying to find the height, what you'll do is you take the volume, you take this volume, then you divide by the cross-section area. So this is C, this is not S, this is C. So take volume divided by the cross-section area. That's when you'll find the height. Okay, to take the volume divided by the cross-section area. Now in this case, this area here, this one represents the cross-section area. Now in this case, let us find the volume. So the volume of this oil drop will be the cross-section area, which is the area of the patch, which is this one that we have just written here. So is equals to area of patch multiplied by the height. The same way as we have seen here, finding the volume of this cylinder is cross-section area multiplied by the height. So here we use the area of the patch, which is this one here, multiplied by the height. So if we substitute this formula, it will be like this. It will be pi, this one will be in brackets d divided by 2, all of it squared multiplied by height. So all this is finding volume. So what if you want to find height? So we said height, this one is equals to volume divided by cross-section area. So the height here will be, we just put this as the subject formula, so we divide by this. So we divide all sides by this value here. So it will be V divided by pi, open the brackets, d over 2 squared. So let me create some space here so that we can continue. So we say that h is equal to v divided by pi into brackets d all over 2 squared. So if we substitute this denominator, it will be h is equals to v divided by pi. If you square d, it will be d squared divided by 4, because 2 squared is 4. Now if we calculate this, it will be like h is given by, so this is like v, you multiply it by So you can put this one on top like this. It will be like 4. Remember, division is like multiplication of the reciprocal of this. So it will be like V multiplied by 4, all of it divided by pi d squared. So this is the formula of finding the height. So if you're given any question about oil drop experiment, finding the height, this is the formula, and finding area, the cross-section area, this is the formula. So that marks it the end of the topic for today. Until next time, bye bye. In our next video, we will look at turning effect of force, so stay tuned. Until next time, bye for now.